All right, all, can you hear me?
I can hear you.
Okay.
Yes.
All right, let's begin. So again, just checking. Am I audible?
Yes.
Yeah.
Yes.
You might hear some odd sounds. There's a dog in the apartment downstairs which likes to howl, and the occasional plane may go by. So if you hear those sounds, just bear with me. Now, what we've seen so far are that MLPs are universal approximators. They can model pretty much any function. And we saw how we could train them to model specific functions. We also saw how we could scan with MLPs to get position invariant detection of patterns, and this gave us convolutional neural networks. Today, we're going to switch to a different topic where we want to model series of inputs. There are many situations where we actually have to consider a series of inputs to produce an output. And the outputs too may be in a series. Here are a couple of examples. Speech recognition. When you're performing speech recognition, you must analyze an entire recording of speech before you can decide what the person said. So here the inputs are sequences of vectors, and the output is a classification result. Or if you were performing sentiment analysis or some kind of classification on text, then here's something. The Steelers, meanwhile, continue to struggle to make stops on defense. They've allowed on average 30 points a game and have shown no signs of improving anytime soon. Now, anyone reading this by itself wouldn't find any hint to the fact that this is referring to a football team. You'd have to infer this from analyzing all parts of the sentence, including the fact that a game has 30 points for a winning team, that teams make stops on defense, and so on. And only after analyzing all of that could you determine that this is football and not basketball, for instance. Or if you were performing machine translation, you would read an entire English sentence and output an entire French sentence once the English was analyzed. Once again, you're analyzing a series of inputs to produce one or more outputs. Or the stock market. Now, you could analyze the stock market. On each day, you get a vector of stock values or stock indices. And after having analyzed the sequence of stock values with these vectors, you must decide whether it's worth investing in some stock for tomorrow or for the future. And this decision must be taken considering how things have fared over time. So again, you have to analyze a sequence of inputs before taking a decision. And in the case of the stock market, you would be taking that decision every single day. So on each day, you'd analyze everything that had happened until then to make your predictions for that day. So these are classification and prediction problems, where you consider a sequence of inputs, input vectors, and produce one or more outputs. And obviously, this can be done using neural networks. So before I continue, a quick note on a shortcut. So Kira, no attendance poll, Zoom will give me everything I need. So a quick note on a representational shortcut. I have been showing MLPs using a figure like the one to the left so far, except those figures have been shown face on. This shows the MLP at an angle of maybe 45 degrees going into the page. If I continue rotating this picture, it's eventually going to look like the figure to the right side on. So each box over here represents an entire layer of the network, and each arrow represents a full connection between two layers of the network. So is this representation clear to all of you? How this actually represents this figure sideways? Okay. So continuing on, this can be more complex. If this network had two inputs, then the side-on figure is going to look like this. If the second input first went through a hidden layer before merging into the hidden layer the next time, the side-on figure is going to look like this. So again, all of this just illustrating the visualization. So let's get back to our problem. We must consider the series of stock values in the past several days to decide if it's wise to invest today, because your prediction about how the stock is going to behave tomorrow clearly depends on how it has behaved in the past. So what kind of model would you recommend based on everything we've learned so far to analyze stock values over a window of time before deciding, before making a prediction? What kind of model would work here? Anybody? A 1D CNN, right? Perfect. So you'd have something like this. You'd have several hidden layers and a final prediction. And this network is going to look at the current input and the past several inputs, and then it makes its predictions. So a CDNN or a TDNN. You guys got it right. And so each day, the network is going to look at a history of a few days and make its prediction. But then this network is a finite response system. Something that happens today only affects the output of the system for some n days into the future, where n is the width of the window that the system is looking at. So here, for example, this network is only looking at a window of 4 days. So if some event happened on day t, as shown by this red box, as you begin making predictions, that event is going to influence your prediction on day t. It will continue to influence predictions on t+1, t+2, and t+3. But then when you get to t+4, that window has slipped past the event. And so the event no longer affects the output. So the response to any event only lasts for a finite amount of time. So this is a finite response system. Now, clearly, just having a window of 4 days, considering only the past 4 days to make stock predictions, is very unwise. So just give me a second. Let me shut my window. Maybe the dogs will sound less loud. So looking at a window of just 4 days to make stock predictions isn't wise. because you know that market trends have longer patterns. They have, for instance, weekly patterns. Things change, and you know what happens on Monday predicts what happens on next Monday because things change over the weekend. The entire market slows down over weekends, and so on. So if you wanted to make this model consider a window of 7 days, what would you do? This one. Anyone? How would you make it consider a window of 7 days? Anyone? Just increase the window size, right? N equals 7. And so you can keep considering, you know, longer and longer windows. We also know that there are monthly trends. People tend to spend more money on the day on which they receive their paycheck. And so to consider that, this window would have to extend to 30 days. But then you have even longer trends. You have the weekly trends in the market, monthly trends, you have annual trends. What happens? Yeah, the shopping spikes every Thanksgiving. And so the shopping pattern of this Thanksgiving tells you something about what you may expect next Thanksgiving, and so on. So if you want to consider all of these long-term historic trends, then the size of the window will have to keep increasing. In the limit, you really want to consider everything that happened in the past. And this window would get really large. So what would be a problem with this kind of a model? What would be the problem here? Anyone? The number of parameters is going to increase absurdly, right? So here is our first poll, if I can release it. I have 60 seconds, folks. All right, 10 seconds. Okay, we can end this. So here are what we got. Now, can you tell me what the answer to the first question is, true or false? True, right? What about the answer to the second question? False. So I'm kind of surprised that a whole lot of people who said convolutional networks are finite response systems also marked true for the second statement, which says an input at time t affects the output for all time. Clearly, these two are contradicting one another, right? If it's a finite response system, then by definition, something that happens at any time has a finite window of time during which it can influence the output. And that is the issue with convolutional neural networks. And even if you have the entire distributed representation and such like that we saw in the classes, eventually a CNN is just scanning with an NLP. And the NLP has a finite width of input that it considers. And so a CNN is a finite response system. Now, what we want is an infinite response system, something that considers the infinite past in making its predictions. And here's a very simple infinite response system where the output at any time is a function of not just the current input, but also the output at the previous time. Now, of course, for this to work, you need to define y of -1, which is the initial state at time t equals 0. But then once you do that at each time, the output at that time is fed as an additional input to the next time. So an input at x0, which is at time 0, produces some y0. But then y0, even if there are no further inputs, because you have y0, y0 will result in some y1, then y1 will result in some y2, and so on. And so a single influence is going to single input is going to continue to influence the output for the rest of time. Now, this sort of network is what's called a NARTS network, or nonlinear autoregressive network with exogenous inputs. Now, why is it autoregressive? The term autoregressive refers to the fact that the output at time t minus 1 is fed back to compute the output at time t. So the outputs are regressing on itself. And so here's what the network is going to look like. At any time t, the network would make a prediction, yt. But at the next time, the next input and both the previous prediction are going to go into the network. And so, and then it will make its next prediction, which is then fed in along with the next input at the next time to make the next prediction, and so on. And so, as you can see, an input at any time continues to influence the output for the rest of time, even if there are no subsequent inputs. That makes sense? What we just did? Okay. So does this network have memory of the past? Where is the memory? Is the memory in the network, or it's in the previous output? So the memory is no longer in memory is not anywhere within the network. The memory is external to the network in the previous output, which has aggregated things from the past. So I'm going to, instead of having a separate yellow box over here, I can just draw the figure like so. These two figures are the same. That the output layers output feeds to the next time. But the fact that we all stated remains that this network has memory, but the memory is only stored in the output, in the latest output. Now, of course, you can make this what is nonlinear because all of the activations are nonlinear. That's why. Now, you can make this network arbitrarily complex. At any time, it could be considering both the current input and a whole bunch of past inputs, and a whole bunch of past outputs. But nonetheless, so this would still, but this would still be regressing over its own outputs over time. So this here is a first order autoregression where it considers only one past output. This is a higher order autoregression where it considers several past outputs. So these NARTS networks were historically very popular for time series prediction, and they were used in predicting the weather, stock markets, in tracking systems, and in language. Basically, any phenomenon where you have some pattern and some additional inputs that modify this time series pattern. And the key here was that the memory of the past is in the output itself and not in the network. So it makes sense. We'd like to make the memory more explicit within the network itself. How can we do that? Again, remember the task is to remember the past. So let's introduce. Yeah, that's correct. So this would be, for example, it's this figure. If you receive inputs from the past K outputs and the current and past L inputs, then this would be a KL order NARTS network. Anyway, going back, what we really want is to be able to remember the past, but somehow we want some variable within the network that keeps track of the past. So an obvious thing to do is to introduce an explicit memory variable whose job it is to remember. And so the memory variable now is going to be some function of the past outputs, the past hidden states, and past memories, because you're always building on memories. The hidden state at any time is now going to be a function of both the current input and what was in memory. And the output itself is going to be a function of the hidden state. So this is what the network would look like. This was called a Jordan network, proposed by Michael Jordan, who's now a professor in Berkeley. He's famous for other work, but his thesis was on these Jordan networks, which introduced the concept of memory into neural networks. Now, the thing here, what the Jordan network does is a very small increment over the Knox network. In the Knox network, if I had a first order Knox network, you were only looking at the past one output. Even if I had a higher order Knox network, you were looking at the past few outputs, but you were not considering all infinite outputs in the past. Now, if you want to consider all infinite outputs in the past, you would either have infinite taps into the Vice, or here's what you could do. You can just have this little block over here, which maintains a running average of the outputs. So at any time, it's going to be updating itself as some mu times its past value plus the latest output. And this block is what feeds into the hidden layer at the next time when it makes its prediction. So this was the famous Jordan network, where you actually somehow considered all previous outputs when making the next prediction. Now, the memory itself has a fixed structure. There's nothing learned about this memory. All this block does is to maintain a running average of outputs, and that is fed into the network for making the next prediction. So when you perform back propagation, there's nothing going back from here. This is just a running average operation. Does this make sense? Questions? Okay, there's a single Y. I'll take that as a yes. Now, what's the obvious next thing to do? Instead of just, this is still recursing on memory, right? What we wanted to do is to transfer the, so Mariam, this just means that if you're feeding just one output, you're just considering the latest output. This is looking at all infinite past outputs in some sense. Did that answer your question? Right. So what we wanted to do is to actually have a variable within the network that stored the memory. So that's what Jeffrey Ellman came up with in 1990. He introduced something called a context state. All the context state did was to clone the hidden state from the previous time. And this cloned hidden state from the previous time was fed into this hidden state, was used to compute the hidden state at the current time along with the current input. And this hidden state was used to compute the next output. Then at the next time, this hidden state was once again cloned. And this guy would be used to compute the output at the next time. So you're actually using the hidden state in the network itself as a way to carry memory. But the way this was set up, this is actually being cloned. This guy was being cloned over here. So when you perform backprop, for instance, at this time, the gradient would pass backward. It would go up over here. And so you would update these weights maybe. But then there was no further transfer of gradients, propagation of gradients back from this context unit into the previous time. So this entire sequence of inputs was used as a collection of single instant predictions, where at each time, along with the current input, the hidden state of the previous time was also an input. And so this was what was called a partially recurrent network, because although in the forward pass, you're actually carrying information through the hidden states. When you're learning the network, all the updates are being done locally with no gradients being passed backward through time. Did this make sense? Yes or no? So the idea of memory is you want something in the network which keeps track of everything that it has seen over time. So that was that is the requirement. Now, how many layers neurons would such one of these networks have? Well, we're going to go some distance, so we'll answer that later. But what exactly is cloned? Consider this network. You have an input, you have a hidden state, which is computed from the input and this guy, and the hidden state will take some value. This value is just cloned. You just copy it over, that's it. Right? So Again, Jessica, remember that if you have an input over here, so we don't. In this model, they did not. Hector, you're predicting my next slide, right? So to answer the question, you can see that any input over here is going to continue to influence outputs for the rest of time because of this cloning. It's just that errors out here are not back propagated all the way here because there is no back propagation over these jagged edges, right? So the output of the hidden layer is cloned into the navy state, into the navy layer. That answer you, Chris? Okay, so this obviously leads you to the question, why? Why clone, right? Why clone and why not pass the gradients back directly? And that's what we will do next. So the story so far, in time series analysis, models must look at past inputs along with the current input. Looking at a finite horizon of past inputs gives us a convolutional network. Looking into the infinite past requires recursion. Knox networks recurs by feeding back the output to the input and may feed back a finite horizon of outputs than the inputs too. Simple recurrent networks, Jordan networks maintain a running average of outputs in a memory unit. L1 networks store a hidden unit value for one time instant in a context unit. It's simple or partially recurrent because during learning, the current error does not actually propagate to the past. So what makes this better than the Jordan network? What makes it better here is really the fact that these things can be arbitrarily complex, whereas this is just going to be a simple prediction. Your hidden state can be very complex. Did that answer your question, Leon? Yeah. Okay. So this blocking of gradients doesn't make sense because when you're analyzing a time series, sometimes an input here may influence the output way out in the future and not really make much of a difference all the way until you get way out into the future. So in order to learn these influences, you need to be able to propagate errors all the way back to time. And so for that, we need a slight modification to the network. And we'll get to that next, but first the spoke. Not really, Miguel. We never use cloning of this kind anymore in most architectures. We actually use the values because we like to propagate errors backwards. Okay, 20 seconds. All right, let me stop this. Okay. There was much confusion about the first question. First question, true or false? Do memory neuron models have? Why is it false? False is correct, but why? Why? Because you have recurrence going forward in time, but you don't have recurrence going backwards in time when you're propagating gradients backwards. So recurrence occurs only in one direction, but not the other. And what about the second one? True or false?
Huh?
Yeah. Was there a question?
That is the oh.
I'm not sure if somebody's asking me a question, so I shall continue. Right? False and true. So you must have had this thought in mind. Why not have the recurrence going backward as well? And so that gives us the state space model, which is what we have in current modern recurrent neural networks. Now, instead of simply cloning the hidden state and making another copy of it through which gradients are no longer passed back, we actually directly make the hidden state at any time a function of the hidden state at the previous time. So this is the state space model. In this model, there's a hidden state which is recurrently computed based on the current inputs and the hidden state at the previous time. And the output is computed only based on the hidden state. So HT is the state of the network. It summarizes information about the entire past. So the model directly embeds the memory in the state. Of course, for this to want to work, in order to be able to compute H0, you need to have an initial state H minus 1, which you can think of as a parameter of the network. Now, this is a fully recurrent network, or simply a recurrent neural network. Why? You will see this shortly. This is what the computation is going to look like. At any time t, the input and the hidden state at the previous time are used to compute the current hidden state. And the current hidden state is used to compute the current output. So if you had a sequence of inputs, this is what the computation looks like. You have the initial H minus 1. That and the 0th input are used to compute the hidden state at time 0, which is then used to compute the output at time 0. Then at time 1, the first input and the hidden state at time 0 are used to compute the hidden state at time 1, which is then used to compute the output at time 1, and so on. So at each time, the input at that time and the hidden state at the previous time are both used to compute the hidden state at the current time, which is then used to compute the output. So this H minus 1 can either be set fixed to 0 or something of that kind, or it can be learned as part of training. Both of these are done. So now you can see through these arrows. If I had an input at time 0 and no further inputs, look at what happens. This input is going to influence this hidden state, and then that influence stays forever and affects the output. So an input at time 0, yes, that's correct. So an input at time 0 affects the output forever. And so this gives us full recurrence. Also, because of the way it's set up, anytime you find an error happening here, if you were propagating derivatives backward, it would propagate all the way back to the beginning. So you have complete recurrence both going forward and backward. This is a fully recurrent network. Is this picture making sense to you guys? And the idea behind it? Okay. So now in this figure, I've just shown you a very simple single box for the hidden state, but the hidden state can be arbitrarily complex. It can have many layers. It can have all kinds of connections, just so long as we define the H minus 1 according to the setup, we are fine. So here are some examples. Here's a recurrent neural network where the hidden state comprises a single hidden layer. So what a small influence in the H, it depends on the parameters of the network. So we can answer that question at the end of next class. Now, in this model, the hidden state has just one single hidden layer. Now, every column is identical to every other column because each column is using the same computation to compute its output as every other column does. The only thing that changes are the inputs, namely the actual input itself and the hidden state at the previous time. Now, here's a slightly more complex model where the hidden state actually has two layers. And correspondingly, you're going to need both of those layers defined at time minus 1 for initialization. Or here's an even more complex network where you have skip connections. It doesn't matter. If I can just put all of these central regions into one green box, you have the input going into the hidden states and the hidden states feeding the output. Or you can have something like this. So I don't want you to get the idea that things can only go, left to right, bottom to top. Here I have things crisscrossing, and yet this computation is fully feasible. Can you tell me why? Why would I be able to compute this guy even though I have arrows going both up and down? Anyone? Can you tell me? The arrow is only going right. So I have all the inputs necessary to compute this guy when I compute this one, which is this and this, because these have all been computed. So also I have all the inputs needed to compute this box, which is all of these guys and this one. So you still know everything since there are no arrows going backward. Perfect. Again, the point is that the hidden state can be arbitrarily complex, and there's no need to restrict yourself to looking at back only one time step. You could be looking back multiple time steps. The only distinction is that now you'd have to define your initial values for as many time steps as you look backward for. And that's it. And once again, all the columns are going to be identical because each column is performing the same computation. Now, in practical implementations, we typically use the simplest structures like this one over here, where the hidden states are just a sequence of layers. So, any questions so far? Any questions? No. Oh, okay. The more complex, again, at some point it gets to Hector. This gets to be a little bit of an empirical science, and so it will depend on the nature of the problem. For having a structure such as this, you probably have to justify having to go back down. For having a structure such as this, you would need to imagine that the recurrence is deep and has multiple modes. Now, once again, we can return to this in the next class because we'll discuss some of these issues, right? Anyway, when you actually look at the older books on neural networks, this is how they would depict recurrent neural networks. So this one is a single hidden layer recurrent network, and this red arrow looping around, it doesn't mean that the output of this layer is going back in. It means that there is a recurrent connection over here. So also this network with two hidden layers has recurrent connections in both layers. So does this, right? And so if you consider this one, this figure, the actual computation looks like this guy unrolled over time. So as you unroll it, this red arrow keeps getting repeated like so. And so this is the actual computation being performed by this recurrent neural network. At each time, there's a single hidden layer, which is computed from the current input and the past value of the hidden layer. This one here, again, the actual computation is like having this network unrolled over time. And so at each time, you have two hidden layers. Each hidden layer is computed from either the input or the hidden layer below it, and the same hidden layer at the previous time. And the final output is computed from the final hidden layer as given by this architecture. Or this guy, again, you can just see that the actual computation is just this picture unrolled over time. So this, you'd be unrolling this red arrow again and again to get these horizontal arrows. This is just to explain the visualization, the pictorial depiction of such networks. Now, what is the actual computation performed? Here's what it looks like. Let's consider this simple network with a single hidden layer. At each time, you have an input, and the hidden state is computed by applying an activation to an affine function of the current input and the hidden state at the previous time. The output is computed by applying another activation to an affine function of the hidden state at that time. By an affine function, we really mean a weighted sum of all of the components plus a bias. So observe that for the hidden state, the affine function has two components. One is the term coming from below, the weighted sum of inputs. The other is the term coming from the left, the weighted sum of the hidden state at the previous time. So there are two sets of weights. This first set of weights is the set of weights associated with the vertical arrow. These are the current weights. The second set of weights is the set of weights associated with the horizontal arrow. These are the recurrent weights. Is this making sense, guys? Yes or no? Okay. Same thing here. If I have two hidden layers in the hidden state, then the first hidden state is computed by applying some activation to an affine function of the current input and the same state at the previous time. The second hidden state is computed by applying a different activation to the first first hidden state at the same time and the second hidden state at the previous time. And the final output is computed by applying an activation to an affine function of the second hidden state. Now over here, can you guys identify the current and recurrent weights in this picture? Which are the current weights and which are the recurrent weights? Anyone? So W1 and W2 are current, right? Exactly, because these are these vertical arrows. And W11 and W22 are the recurrent. So you can make out their recurrent by considering the fact that W11 is multiplying h of t minus 1. So obviously it's dragging things back from the past. W22 is also multiplying h2 of t minus 1. So it's dragging things from the past. So these are recurrent weights, whereas W1 and W2 are considering x of t and h of t, which means they're only looking at the current time. Does that make sense? Yes or no? Right. And so also I have some equations for this third architecture, just for reference, right? So we get a basic idea of what recurrent networks are. And they can be applied for various kinds of tasks. I got this, I don't remember where I got these pictures from. These are from Andre Karpathy. But they're a brilliant depiction of the things you can do. So here's your standard MLP. Each input generates a single output and only refers other things at the same time. So there is no recurrence over here. But then you can have something like this, where you have a single input and the recurrence produces a sequence of outputs. So this could be, for instance, an image captioning problem, where I give it an image and it generates a sequence of words. Or you can have a sequence of inputs, and when you run out of inputs, you generate an output. This could be, for example, for speech recognition. You consider all the speech and then decide which word it was. Or you can have something like this, where you analyze the entire sequence of inputs, and only when they're all analyzed do you generate the sequence of outputs. So this is what I call the delayed sequence to sequence network. And this you would use, for example, in machine translation. You would analyze all the English text, and when you ran out of English text, you know the English was done. Then you can perform the translation, and you would generate all the French text. This last one is a sequential, this is a synchronized sequence to sequence model. This too analyzes a sequence of inputs and generates a sequence of outputs, but then corresponding to each input, there is an output. So this you would use, for example, in things like the stock problem, where on each day, you make predictions about the next day's stock. And so on. So you get the various kinds of problems that we can apply this basic infrastructure for. And so here's the story so far. Time series analysis must consider past inputs along with the current input. And looking into the infinite past requires regression. Knox networks achieve this by feeding back the output to the input. Simple recurrent networks maintain separate memory or context units to retain some information about the past. But during learning, the current error doesn't influence the past. State space models retain information about the past through recurrent hidden states. These are fully recurrent networks. The initial values of the hidden states are generally learnable parameters as well, although they may also be fixed. And the nice thing about state space models is that they enable current error to update parameters way back in the past. That's why they are fully recurrent. Any questions? No. Okay. So far so good. But then how do we train the network? To train the network, we use a technique called backpropagation through time. Now, for the first thing we must notice is that these networks work on input sequences and generate output sequences. So a training pair, which consists of an input and a target output, actually consists of an input sequence, this entire sequence of inputs, and the desired output sequence, which is the entire sequence of desired outputs. And you want to train the network parameters to minimize the error between the sequence output by the network and the desired output sequence. Again, it's not the sum of errors at each time. The desired output is an entire sequence. The actual output is an entire sequence. And the error that we compute is between the output sequence and the desired output sequence. And the network is trained to minimize this error. So, and once we realize that, we also see that this unrolled computation over here is just a giant shared parameter neural network, because all columns are identical and shared parameters, this arrow and this arrow are the same parameter, this arrow and this arrow are the same parameter, this and this would have the same parameters. And so the network parameters can be trained by a gradient descent or its variants using shared parameter gradient descent rules, which we saw several classes ago. And the gradient computation is computed using backpropagation. So for this, you first require a forward pass through the network, and then backward propagation of the gradients and pooling of gradients for parameter sharing. So let's see how this is done. First, what is the forward pass? For each training input, during the forward pass, you're going to pass the entire data sequence through the network and generate outputs. So all of the X's, the sequence of X's go through the network and generate the sequence of hidden states, which generate the sequence of outputs. And what does that look like? Assuming that the hidden state has several layers, here's the simple pseudocode for it. You're going to go from the beginning to the end. And instead of calling this the input, I can call this the 0th layer hidden state. So HT0 is XT. You go sequentially through the layers and of the hidden states. For each layer, you compute the affine term, which depends on the same hidden state at the previous time. The same hidden state at the previous time, this is the recurrent component. The hidden state in the lower layer at the current time, which is the current component and the bias. And this hidden state, this affine term is put through an activation function, typically a tanh activation function, for reasons that we will see in the next class, to compute the hidden state. And so then the hidden state of the Lth layer is passed on to compute the hidden state of the L+1 layer using this formula over here, from which you compute, to which you apply the activation to get the hidden state of the L+1 layer, and so on. When you get to the final hidden state, once again, we compute an affine term and put it through a softmax to make the predictions. Now, all of this is just sort of to give you an idea of the fact that although the pictures are simple, the hidden states are in fact multi-layered, can be multi-layered. The computation is not anything incredibly complex. It's just like an MLP. The only extra magic was that within each layer, we had this recurrent component, which looked at the value of that layer at the previous time. So once the forward computation is done, all of these Ys will be available. Then for each training input, we are going to perform a backward pass, going from the end to the beginning, and compute gradients through backpropagation, which is why we call this backpropagation through time. So now this figure gives us some kind of a, it could be interpreted somewhat bizarrely, because I have this block over here and I have arrows going in from the side and the bottom. And that might not make it clear that in fact, both of these are just inputs to this box. So to make it more obvious, I'm redrawing the picture like this. The output of the hidden block at each time goes both to the output layer and to the hidden state at the next time. And at each time, the hidden state gets two inputs, the hidden state at the previous time and the input at that time. So this is just a redoing of the illustration to make the connections obvious. And now I can color these connections. Because every column is identical to every other column, all of these arrows shown in blue have the same set of weights. If a training run updates the parameters here, obviously it updates all of these because it's updating the recurrent network itself. So also all of these red arrows have the same parameters. All of these green arrows have the same weights as well. So in this particular figure, there are three sets of shared weights, and those are what we will be learning. The output is going to be a sequence. The desired output is going to be a sequence, and the divergence is going to be computed between the sequence of actual and desired outputs. And this is not necessarily the sum of the divergences at the individual times, unless we explicitly define it that way. So is the setup clear, guys? So why is it incorrect to assess errors individually? Again, Miguel, this is a time series model, right? Now, let me give you an example of translation, machine translation. I can generate a sequence of words. The desired sequence of words may be different, right? Can you find a one-to-one correspondence between the words you generate and the words you desire? Would you be able to do that, Miguel? So basically, you have to define that you have to agree that this is just a divergence between two sequences, and it's, you know, in the abstract, we cannot really say, we cannot make a one-to-one correspondence between the actual and desired outputs. And so it's really hard to decompose most divergences into the sums of divergences at individual types. We will see in the coming classes how we can actually convert one of these complicated situations to a situation where the divergences can be considered at individual times, because that's what makes the computation simple. But in principle, this divergence is between two sequences, right? Okay. That clear? Huh? Is that clear, guys? Okay. And now, so Vinayak, to answer your question, this is the same recurrent network being used at each time, correct? Vinayak? So that would
Yes.
mean that the weights over here are the same as the weights over here, right?
Okay.
So all of these blue arrows represent the same set. Okay, now let's see how the back propagation happens. I just labeled a few variables. By t is the output at time t. And there's a subscript I just to indicate the component, which I won't actually use. Z superscript 2t is the affine term over here. H of t is the output of the hidden layer here. This affine term is computed from H of t at any time. Z1 of t is the affine term at the input to the hidden layer. And X of t, of course, is the input, right? So we're going to have all of these weights. We're going to have the current weights from the input to the hidden layer and from the hidden layer to the output. That's W1 and W2. We're also going to have the recurrent weights associated with this red arrow, which is W11. These are the things we must learn. I haven't explicitly shown the bias, but those would be included in the weights. So where did I lose you guys? Okay. Did you understand the notation here? Did you have this slide? Yes or no? Okay. So this is just the notation. at any time, so I'm using different notations. Z's are the affine terms, H are the hidden states. So over here, Z superscript 1 is the affine term at the input to the hidden state activation. And H is going to be the output of the hidden state activation. The term within the parenthesis represents the time. Similarly, Z superscript 2 represents the affine term at the input to the output activation, and Y represents the actual output. Did that make sense? Did you get that? Right. Okay. And there wasn't anything lost, right? And so here are some additional terms. The weights of this network, the parameters of this network are W superscript 1, representing the current weights from the input to the hidden state. W superscript 2, representing the current weights from the hidden state to the output. And W11, representing the recurrent weights. These are the terms we must learn. And I'm not explicitly showing the bias, but the bias must be learned too. Make sense? All of this clear? Okay. And so move on, right? Here, the thing is, no matter how you compute the divergence is an error between the actual sequence of outputs and the desired sequence of outputs. That divergence function must be differentiable with respect to each one of these outputs. Otherwise, the whole thing breaks down. And so we will see in coming classes how we make that happen in order to be able to train these networks under different settings. But for backprop, assuming that the divergence is differentiable with respect to this yt, then we would start off by computing the derivative of the divergence with respect to yt. So then, and again, computing this can be a challenge. We'll see how to deal with it in following classes, right? After this, we're going to use two simple rules. The first is the chain rule for gradients. If I have y influencing z, influencing y, and so on, and eventually influencing a loss, the derivative of the loss with respect to z is going to be the derivative of the loss with respect to y, right, multiplied by the derivative of y with respect to z. So also the derivative of the loss with respect to yi minus 1 is going to be the derivative of the loss with respect to z, right, multiplied by w. Do you remember these rules? Do you remember these rules, guys? Also, for the weights, we saw that the derivative of the loss with respect to the weight was simply this y times the derivative of the loss with respect to z. That's this guy. We saw this in class as well, right? So these are old rules. We've already seen this. We're going to reuse those. So also over here, if y goes out through multiple paths and influences L, then the derivative of y, the loss with respect to y, must sum over all the paths. So it will be the derivative of the loss with respect to z, z1 times w1, plus the derivative of the loss with respect to zi, times the derivative of the loss with respect to zi plus 1 times w2, right? So this again is the distributed chain rule. You remember this, right? Yes or no? Okay, so let's see how this goes, right? After this, it's very easy. We've assumed that we've already computed the derivative of the divergence with respect to yt, somehow magically, because that's how we've defined the divergence. So the first step we are going to do, starting at the end, is to move a step down and compute the derivative of the divergence with respect to the affine term here, z2. Ignore the pictures in the text in yellow. Those are just the scalar versions of the derivatives. So the derivative of the divergence with respect to z2 is going to be the derivative of the divergence with respect to y times the Jacobian of this activation function. You remember that? Yes or no? Or have I lost you guys? Okay. And then what would I compute next? Once I have the derivative here, what would I compute next? Anybody? Which way would I go? Okay, let me help you with this one, right? The next thing I'm going to do is to backpropagate and compute the derivative. I have the derivative of the loss with respect to z at this point over here. So I'm going to backpropagate and compute the derivative of the loss with respect to h here, correct? And what is that going to be? That is simply going to be the derivative of the loss with respect to z, the divergence with respect to the z times this weight. Correct? Yes or no? Yeah. Right. And then I also need the derivative of the loss with respect to this weight matrix. What will that be? Anybody remember? What is the derivative of the loss with respect to this weight matrix? We saw the formula a couple of slides ago, right? This guy here. So that is simply going to be this here, which is going to be this h times the derivative of the loss with respect to this z. Do we remember that? Actually, h times the derivative of the loss with respect to z, column vector notation. Vinayak, you have the row vector notation, right? So we've computed derivatives out here. Then what? Then I have to take a step back and compute the derivative with respect to this z, right? And the derivative with respect to this z is simply going to be the derivative with respect to h times the Jacobian of this activation. And so now we have the derivative here. That clear? This one? Yes, no? Yeah, okay. And then what do I do next? I need the derivative with respect to these weights, right? And that is going to be, what would that be? Anyone? Just trying to jog your memory. Not that it's very important, but you've been through this a few times, homework 1 and so on. So what is the derivative of the divergence with respect to these weights? Okay. Since I'm running out of time, let me answer you guys. That's simply going to be this x times the derivative of the loss with respect to this z, right? So I have got these guys. Then if I'm propagating backwards, what is the next derivative I need to compute? It turns out I'd have to start from here, okay? And so the next thing I would do is first, I also need to compute the derivative with respect to these weights. And that's simply going to be this h of t minus 1 times the derivative of the divergence with respect to this z. That's the derivative for these weights. Did that make sense? That's h of t minus 1 times the derivative here. Right. Okay, so we finished with the last column. Then we take a step back, right? And I'm going to go down this line and compute the derivative of the divergence with respect to, I already have the derivative of the divergence with respect to yt minus 1. Again, remember, I assume that derivatives are available for all of these guys, from which I can compute the derivative of the divergence with respect to the z2 simply by multiplying this derivative by the Jacobian of the activation here. And then I can take a step back. And here is the here is the important thing. This output took two paths, one up and one to the right, correct? And so the derivative here has two additive components. One is the derivative which came down here, which is the derivative with respect to z2 times this current weight, plus the second derivative which came out this way, which is the derivative with respect to z1 times the recurrent weight. That makes sense? Over here. Did this make sense, guys, this equation? Okay. That's just 4 people. What about the rest of you? Is any, okay, 5, 6, 7, 8. Thank you. So far so good, right? Nothing has changed from your standard computation so far. But then here's the thing. I now compute the derivative with respect to the weights for this blue arrow. But then I already have a derivative with respect to the blue arrow out here because these are shared parameters, right? So when I compute the derivative of the divergence with respect to these weights, I'm going to actually be adding them to the derivative that I got out here. So the derivative of the divergence with respect to W2 is going to be the previous value we had for the derivative from the next time instant, plus the local term, which is ht minus 1, times the derivative of the divergence with respect to z2. So did the summation make sense? Yes or no? Because it's a shared parameter network. And so that was one change here, right? Then I can pass the derivative back here. I already have the derivative with respect to h. I can just multiply it by a Jacobian. So I have the derivative with respect to the z. And now once again, when I compute the derivative with respect to the weights here, these are the same as the weights out here. So the derivative of the divergence with respect to W1 here is actually, it already has a value and I'm going to increment it by xt minus 1 times the derivative here. So this is the local derivative. I'm adding it to the value that I already had. So this making sense here? Because these two green arrows are the same thing, right? So what about for this red arrow? What would happen? Yeah. Are these red arrows shared too? Yes or no? And so we're going to see that out here, the derivative of the divergence for this recurrent weight is going to be, it already has a value from here, it's going to be incremented by the local derivative, which is the ht minus 2 times the derivative at zt minus 1, right? So we managed to get the derivatives here. And then I can go back and go down the next column and the next column and keep using the rules and continue computing derivatives until I get all the way to the beginning. And eventually I can also compute derivatives with respect to h minus 1, which means that h minus 1 can also be learned. Did this whole thing make sense? I don't expect you to remember the equations, just the basic idea of what we did, and that since parameters were shared, we were actually incrementing the derivatives for parameters. So here's the entire set of equations for the backprop. It's on the slide for your reference. And I also have some pseudocode for it, which I will skip. But it just explains everything carefully. And so it would make sense for you guys to look through it, look through this, because you're going to do this in your homework. So any questions? Any questions? No. Okay. So here's a poll. Sorry. So what's the answer to the first question? True or false? Would you be updating after each input? What was the actual input? The input was the entire sequence, correct? So you'd have to process the entire sequence before you made a single SGD update. Again, your training instances comprised sequences of inputs and sequences of target outputs. So if you process the input, you'd have to process the entire sequence before you made a single update. Did that make sense? Yes or no? Yeah, right. The time step is just one vector, but you'd have to process the entire input. And so in the divergence we minimize is it the sum of the divergences for the individual inputs? Or is it the divergence between the sequence of outputs and the desired sequence of outputs? Which of these two is correct? The first or the second? Yeah, I emphasize this, right? We are always minimizing the divergence between the sequence that we output and the desired sequence that we output. Okay? So these are the two cases. So far, so good. So on to the final topic. Now, all of that stuff that we've discussed so far assume that a left to right recurrence. But in many problems, you have access to the future. For example, if I'm performing part of speech tagging in a sentence, Jules, no, we just have the polls, right? So no, so when we're performing part of speech tagging, then I see not just the current word, I see the entire sentence. And now the information about whether a particular word is a verb or a noun is not just in the words that preceded it, but also in the words that followed it, right? So I'd like to consider both the past and the future in analyzing any given word. And I can do that simply by, having this guy look both at the past input and directly look at the future hidden state. If I did that, then what would happen? If each node looked directly both at the past and the future, in this case, what would happen? What would we get? We'd get loops, would we not? Exactly, right. So you can't have things looking both into the past and the future in a naive way because you'd end up with loops. This influences this, influences this, influences this. You're never going to get to the end of that computation. So what we do is we break up the forward and the backward dependence. This is our bidirectional recurrent neural network. Within any layer of this bidirectional recurrent neural network, you have two components: a forward net, which processes the input from the beginning to the end and has this initial value h-1, and a separate backward net, which processes the input from the end to the beginning. So here's how the computation is done. When the input comes into the layer, the forward net is going to take all the inputs and simply process them in sequence, left to right. Then the backward net is going to take the same input and process them in sequence, right to left. And then finally, the outputs of both the forward and backward net are going to be concatenated or combined in some other way to give you the final output of the layer. Is this computation making sense to you guys? Yes or no? Yes. That's one. What about the rest of you guys? I'll wait for a few more, right? And do you see how this avoids the problem of loops? Can you see how, right? Because the forward and the backward computations are done end to end without invoking each other within any layer. And of course, the entire network can be formed by stacking one or more of these bidirectional blocks, followed by a final. They can, like I said, you can just concatenate the outputs or sum them or do anything else. Concatenation is probably the most common way, right? So, and then the entire network, of course, is going to have many such layers. Now, again, the forward network and the backward network individually might have multiple layers, though typically they tend to be just one layer. So, is this making sense? All of this? Yes or no? Okay. It's a small number for this. How is the loss function? The loss is still the loss between the final sequence of outputs and the desired sequence of outputs. Did that answer your question, Jules?
Yes.
Okay. What's the advantage of doing this? Like I said, if I'm doing part of speech tagging, if this is a word, the information about its part of speech can be inferred from both the words in the past and the words in the future, correct? In many data points, just as the past influences the future is also predictable from, just as the past influences the current, you can also make deductions about the current based on how it affected the future. So you can look at the future and make deductions about today, and you can look at the past and make deductions about today. So this is combining both. Now, how would you do back propagation on this? Before that, let's do a poll. Final poll. Okay, 15 seconds, guys. Okay, 5. Let me stop this. Again, lots of confusion over here. So here's what we look at. You're saying, and okay, can someone tell me the answer to this one, true or false? So those of you who say it's false, you're correct, but why is it false? Future data are not available, right? A day trader, if he's trying to make predictions, he cannot use a backward network because the backward network needs to know things that happened after today. And that data doesn't exactly, the trader doesn't have a crystal ball. So this cannot be, right? I would be rich if I could see the future data. So this can only be used in problems where you have the entire input data, like in part of speech tagging, speech recognition, and so on. So I have some, so I have some pseudocode for it. I'll skip that, okay? Let's go straight to back propagation. So now this might seem like it makes back propagation tedious, difficult, but then think about what happens. After you've done your forward pass, you have all of these edges, and these can be propagated through the network, and you get the divergence. In the backward pass, at any layer, you're going to start off with the derivative of the divergence with respect to the output of the network, output of the layer. The output at each time, the output of the layer was actually the concatenation of two outputs. It was the concatenation of the output of the forward and the backward blocks, right? So this derivative is going to have the same size as the concatenation of these two outputs. And so I can split this derivative into two portions. The first portion corresponds to the output of the forward block that was included in the output of the layer. And the second portion was the output of the backward block that was also included in the output at that time. And so from this derivative, with respect to the output of the layer, I can get the derivative at each time with respect to the outputs of both the forward and backward blocks. Is this making sense? Over here? Okay, no, so consider this. How did we combine the forward and backward block outputs? So let's say this produced a three-dimensional output, and this produced a three-dimensional output. The output of the layer would have 6 dimensions, right, Christine? Yes or no? Okay. When you come back, the derivative of the divergence over here is going to have as many components as the output of the layer. So it would have 6 dimensions also. Yes or no? Yes. And the first 3 components are therefore attributable to the forward layer, and the last 3 components are attributable to the backward layer, right? Because the first 3 components of the output were from the forward layer, and the last 3 were from the backward layer. And so I can just separate out the first 3 exactly. I can separate out the first 3 components and pass them here, and the last 3 components and pass them here. And so now I have the derivatives of the divergence with respect to the outputs at each time for both the forward and backward blocks. That makes sense, right? And thereafter, the rest is simple. In the forward pass, I can just use your standard backprop, except I'm going from end to beginning. In the backward pass, I can use the standard backprop, except I'm going from beginning to end, because here the computation was from end to beginning. So the derivatives must go the other way. Did this make sense? Over here. Yes, and so at the end of it, you're going to have the derivative of the divergence with respect to the input at each time of the forward block. You're also going to have the derivative of the divergence with respect to the input at each time of the backward block. But because this x is going to both, the actual derivative of the divergence with respect to x is going to be the sum of the derivative you got over here and the derivative you got over here. This makes sense? And voila, we have just managed to get the derivatives with respect to the input to the entire layer. So I have pseudocode for the same thing. I'll skip that. But the thing is, now we can just continue back propagation as before. And so we also know how to train the network. And so to summarize today's lecture, time series analysis must consider past inputs along with the current input. Recurrent networks look into the infinite past to a state space framework. These are hidden states that recurs on themselves. Training recurrent networks requires defining a divergence between the actual and desired output sequences, backpropagating gradients over the entire chain of, and then backpropagating gradients over the entire chain of recursion. This is backpropagation through time, and pooling gradients with respect to individual parameters over time, because the unrolled network is a shared parameter network. Yes, Jules, yes. So bidirectional networks analyze data both ways, beginning to end and end to beginning to make predictions. In these Denver networks, backprop must follow the chain of recursion and gradient pooling separately in forward and reverse nets. So that's and so these models, they're really great for time series analysis, time series prediction, classification, sequence generation. We'll see more of these in the next class. I'm done for today. Any questions?